Hello, welcome to the second lecture of Module 1. Here, we will try to understand the importance of process monitoring in general and then look into statistical process monitoring. Let us start by understanding why do we need monitoring tools at all. For this, consider this typical chemical plant shown here. In this process flow diagram, we can see several unit operations. We can see a reactor, a condenser, a compressor, a distillation column, and a vapor liquid separator. Now, just like any other complex modern chemical plant, there are so many things that can go wrong here which can hamper the smooth functioning of this plant. For example, you may encounter catalyst poisoning in your reactor, which will bring down the production yield, or your compressor here may start showing high level of vibrations, maybe because of bearing issues, or your valve may start to fail, which will lead to flow abnormalities. The avenues for the problems are many, and these problems, as and when they occur, need to be dealt with promptly because any undesired delay in tackling these problems can have dire consequences. For example, consider these two incidents that occurred in US refineries. Now, the incident reports for these incidents clearly mention the negligence of the plant management towards proactive plant monitoring and timely correction of the process faults as the major cause for these incidents. Thankfully, such severe incidents don't occur that frequently. Nonetheless, less dangerous problems do inflict the chemical plant operations on a routine basis. And this is where now it is easy to see the use cases for proactive plant monitoring. It can help you avoid unplanned downtimes due to sudden equipment failures. It can help you keep your plant operations optimal by avoiding significant product quality upsets. Or in general, it can help you in timely detect any unexpected deviations in your plant variable values. All right, how does the status quo with regards to the proactive process monitoring look like in the process industry in general? Well, in most of the scenarios, it relies upon the plant operators keeping track of the critical process variables against their respective upper limit and lower limits. Now, whenever any of these critical process variable go beyond these limits, the alerts show up on the control screens in the plant control room. Now, this is not adequate. Why? Because your plant does not operate around a single nominal point all the time. Your plant load will change, maybe because your product demand is changing. And because of that, other process variables, they will change significantly. Let me just draw a few diagrams here. Imagine that your plant load is showing significant fluctuations. These are normal fluctuations, right? And because of this, your plant variables, let's pick any temperature, let's say, it will show some correlated variations. Now imagine that, let me change the ink color. Now imagine that this particular temperature variable begins to show some unexpected deviations. Now these deviations are normal, are not normal, and they still lie within normal functioning range for this temperature. How will the plant operators be able to catch this? We cannot expect the plant operators to be on the lookout for such small deviations all the time. Only in the lucky scenario that any plant operator was actually looking at this particular variable at the time of the fault that they would be able to catch this problem. Otherwise, this problem will certainly go unnoticed, right? And this is where SPM can help because SPM takes into account the joint distribution or the correlation among the process variables to alert the plant operators if the any plant data begins to show a behavior which differs significantly from the normal behavior of the plant. For example, consider this simple hypothetical 2D scenario where we have two variables x1 and x2. Now, this data point in red, this clearly comes from a faulty data operation because, as we can see, it tends to be deviating significantly from the normal correlation among the process variables, right? But now imagine that this particular plant relied upon monitoring the x1 and x2 variables individually. They will not be able to catch this particular problem. Why? Because this red faulty data sample still lie in such a region that if we just consider the x1 variable, this faulty sample still lies within the normal operating region for x1 and similarly for x2, right? It still lies within the normal operating range. Now, SPM can help you in another way as well. It can analyze the correlation structure of the process variables and help locate the troublesome variables in case of process fault. Consider this chemical plant again, for example. And now imagine that this plant was facing a problem of product purity drift. Now, out of so many variables whose measurements are being taken continuously, how would we know or the plant operators know which variables might be responsible for this product purity problem? SPM can help us answer that. All right. Now that we have motivated enough the use cases of SPM in general, let's take a step back and look at a zoomed out view of the process monitoring technique landscape and try to see where does SPM fit into this. Here you can see in this tree diagram, the techniques have been categorized into statistical techniques and machine learning techniques. Within machine learning, you have classical techniques. So if you have heard of techniques such as support vector machines, decision trees, random forest, k nearest neighbors, those techniques lie here. On the other end of the spectrum, you have artificial neural network based techniques. Now let's come to this statistical techniques. Now by statistical, of course, it's obvious that it involves uses of statistical methods to monitor the production process. And as we had seen in the previous lecture, these are the topics that we are going to cover in this course. These are mainstream techniques and are extremely popular. Apart from this, we will touch upon briefly a few other techniques which are simply an extension of this classical PCA and PLS techniques. Right? All right. Let me now handle one question that might be in the mind of many of you. Why study SPM when everyone is using artificial neural networks and deep learning for everything nowadays? Well, SPM has been and will remain the bedrock of health monitoring for complex process plants. Why? SPM are easy to implement and provide results which are easy to interpret and therefore are widely popular. Simple SPM models can provide you as good, if not better, results as those from artificial neural networks for most of the industrial systems. And this is why we study SPM. All right. Now that we have set the foundation for what we want to achieve via statistical process monitoring, it is time now to start learning how to implement these techniques in practice. In the next section, we will familiarize ourselves with the Python programming language. If you're already well familiar with this, then you can skip those lectures. Otherwise, I will see you there. Bye bye.